find the area between the curves. Y equals sine x, y equals x. X equals, and x equals. X pi over 2 and x over pi. Everybody, these are vertical lines. And if you're going to graph sine, you've got to do it in terms of radians. All right? And it's a little tough because if this is a distance of 3 and I want the scale to be 1 to 1 so we kind of see it, I better put 1 about here, okay? That'd be for the sine curve, all right? And this would be 1. So my y equals x line would look something like this. Do you guys agree? All right, my sine curve, we all agree, would start at 0. And at 90, the halfway point here, pi over 2, is going to be about here, would be 1. And it's going to come back and be 0 here. You guys agree? So I think it looks something like that. All right. And then the curve keeps going, but I don't particularly care, and you'll see why. And then finally, there's the two vertical lines, which I'll do in purple. Pi over 2 and pi. You guys agree? All right. Now, my graph is crappy, and it typically is. All right? But it doesn't have to be great, because really all I have to get out of it is that the area I'm looking for is right here. And I might screw up, all right? And if I have the upper curve and the lower curve switch, I'll just get the wrong sign on the area. Yes? All right, now, I know for a fact that pi over 2, you guys agree this is 1.57, pi over 2, and pi is 3.14. I know this is 1.57 and 3.14 on the y equals x line, so I know it's above. So if I want to just write this and not evaluate it, it's not too bad. The curve goes from pi over 2 to pi of the upper curve, x, minus the lower curve, sine x dx. If I said write and do not evaluate, we're done. But this is one we can actually evaluate. That's good practice on our trig. All right? Definitely a no calculator problem if you're prepping. So I'll take the antiderivative. All right? And I'm going to write this right away. And again, hopefully you think of these in your head at this point. But I'll put them on here so we're thinking about it, because this is the way Mr. Anderson does it. Now, could you memorize the, you can also memorize the integrals, okay, but I just remember the derivatives and think backwards. On the first one, I add 1, so I get x squared over 2. All right, I like this one because if I have negative sine x, what do I get? I get positive cosine, so this becomes plus cosine x for the second one. Evaluated from pi over 2 to pi, and that's implied over both, okay? Don't need the parentheses, but implied over both. Now, here's the thing. I can check it by taking the derivative of this and making sure it's the same expression as agreed, and it is. And then I can evaluate it. Now, it's not a whole lot of fun to evaluate pi. Do we agree? But we'll leave it in terms of pi. So it's going to be pi squared over 2 plus cosine of pi minus pi over 2 quantity squared over 2 plus cosine of pi over 2. And again, we should know these from our unit circle. All right? I draw the unit circle, and it's just the x values because it's cosine. You guys agree? 0 and negative 1. So this is negative 1. This is 0 from our unit circle. And if you're not sure, use your calculator to check. But again, that's one of the skills from pre-calculus we hope to have. And if I do it out, pi squared over 2 minus 1 minus pi squared over 4 divided by 2. So I think it's pi squared over 8 when you get done simplifying the first term. Because it's pi over 4 divided by 2, pi over 8. I can get a common denominator here to find pi terms. And I get a final answer of 3 pi squared over 8 minus 1 as the exact area between those curves. And this is how all these problems work. You have to know the bounds. You got to know the area you're going to get. It's easy when I give you some x equal limits. You guys agree? That sets the limits, right? The only thing you could probably screw up here would be the order of the upper curve and lower curve, and the only difference is if you screw these two up, it'd be negative, and you'd have to deal with it. Okay, you'd have to deal with it because everybody see that 3 times 3 squared is 27 divided by 8. It's like 5 or 3. 3 minus 1. This is a positive value at the very bottom, right? That's one of the things we got to catch. This is a positive value. Then I know my limits were right.
How do you know when you're...
Rolling on, we're going to try to do 3 examples here. Again, there's a couple ways to do this, and I'm going to do it both ways. The hardest part here is remembering way back about how these two curves are going to look. We know they have a shared point at the origin. Do we agree? So I'm going to do x squared first. They share 1, 1, 2. They do. And so that's x squared. Remember the rule, 0.5 squared is 0.25. 0.5 to the 4th power is 0.0625, right? So the more you multiply a fraction, so at 1, 1, these points are going to intersect, but x to the 4th goes under it. I'm going to exaggerate by drawing it really flat. So what happens here is if I want to find the area between the curves, the region is right here. Okay? You see why? It tends between. Now, I tell you what, I'm with what Riley said. She said it's negative 1 to 1. And remember, yesterday I said sometimes we don't want to solve here. We just want to know, what those points are. She guessed and checked in her head until she saw it or remembered how the curves look. Because do we all agree doing this would be a possibility, which would lead to this, which would lead to this, which there are 2 zeros that are 0, which we knew, and then plus or minus 1. I don't want to work this hard. I had all those answers without solving y equals y. But if I write this integral right now, I probably don't want to write it from negative 1 to 1. I can. Yeah, so this is correct. That's the upper curve. Well, I think the upper curve is x squared. What's the lower curve? X to the 4th dx. Now, what do we know about x squared and x to the 4th? What kind of function? They're even functions. So I know these yellow areas are the same. So I would much prefer to do this integral. And it would be exactly the same because we know they're an even relationship. This second integral is much easier to evaluate. Can you see why? Because this is, use 0, and it's actually going to be 0. It's not like it has a cosine buried in it, right? So, let's do the evaluation. This would be set up, but do not evaluate. That is set up, ready to be integrated. So it's x to the 3rd over 3 minus x to the 5th over 5. 0 to 1. Why am I wrong? Right now, there's one more stuff I think I got to add to it. I don't know. I don't need to see it. Multiply by 2. Don't forget to put the 2 there. A lot of times students drop it. You do need to double, okay? It's a shame when you get half the value and I mark it wrong, okay? All right. I love 1 and 0. I love 1 and 0. I can't stress that enough. So I get 1/3 minus 1/5 minus 0 minus 0. And again, I like writing them so I know I'm right. I'm pretty good at math. I see 5/15 minus 3/15. Use your calculator. So this is 2/15, right? Times 2. And the answer to this problem is it has an area of 4/15. Think about it. A little bit more than 0.2. A goofy number, you know what I mean? But that's the exact area between those curves. If you wanted the area of one side from 0 to 1, it would be 2/15. From negative 1 to 1 would be 4/15. Alright, the last one, and again, I'll set up, and then I'll evaluate. I don't know off the top of my head right away what's on top. Alright, I got some guesses, but I'm going to do a quick sketch. And the first thing I hate is I do not want to deal with it written this way. This is how the book wrote it, so I thought it was important we review it. So we recognize this, hopefully, as this, right? And then the first thing I want to do is I want to write it, personally, I want to write it like that. You guys agree? So that I can deal with it. I want it as a line, okay? So I'm going to do that line first. 3, 2, 1, 2, 3, 4, 5, 6. I know the x-intercept's -3. Alright, so there's our line. Maybe I'll call it Cal. Give it a name. And if I do this function in green, it is the root function shifted up 1. And at 4, I know it's 3. Alright, so if I plug in 4, I know it's 3. At 9, it's 4. So I don't know where, but there's definitely some point out here. I'll call it A initially. You guys agree? Where these will cross? Alright, so I'm going to give you a second here. I'm going to pause. Maybe we try to figure out what A is. So I guess this is a point where maybe you keep guessing. Because if you guess 9, you're going to get 4 equals 4. 9, 4 is a common point in these. When you plug 9 in here, square root of 9, 3 plus 1 is 4. When I plug 9 in here, a third of 9 is 3. 3 plus 1 is 4. If you weren't sure, you would actually set this up, right? And then I would square both sides right away. 1/9 x squared equals x. 1/9 x squared minus x equals 0. So you can factor out 1/9 x. So the two answers are 0 and 9. Alright, that's why I factor out 1/9 x, so that I can get that other integer. So we know A is equal to 9. And again, the green is just the algebra you need. But we really should be able to set up this integral right now rather quickly. 0 to 9 are the limits of integration. The top curve is obviously, I'm going to write it this way. Is that okay with everybody? And then the number one mistake, minus the lower curve, which I'm going to have to put the lower curve in parentheses here, because the negative sign is going to distribute. And we can see that positive 1, negative 1 are going to cancel. This is the nice part. So my final setup would be this. Now I probably would give full credit for this. That's set up and not evaluated too. Okay? Depends on the instructions I give. But now, if I want to evaluate this, I have to do the anti-derivatives. And again, I would personally do that step first. I probably would write it, right? So I want to see that it's square root of x. And I'm going to integrate by adding 1 to the powers, right? So here we go. X to the 3 halves over 3 halves minus 1/3 x squared over 2 from 0 to 9. I probably would take some time, personally, and do some simplification. And because I see 0 and 9 are square roots, I know I can plug these in my calculator, but I probably would leave it as x to the 3 halves minus 1/6 x squared. There's really nothing to pull out, so I don't try to simplify it too much. 2/3 times 9 to the 3 halves minus 1/6 9 squared minus, again, you guys see it's going to be 0 minus 0. I love 0. That's why math teachers do examples with 0, because that simplification happens. So I get 2/3 of 27 minus 81/6. You know, I don't know. Suppose 2, that makes 6. So 27 times 4. If it was 25, it'd be 100. So 108 minus 81. 108, 27. 27/6, which simplifies to 9/2. And that's the exact area. 4.5 is the exact area between those curves. And again, I gave you no bounds. Does everybody agree? That's the hard part about these, I think, often for students. I didn't tell you where to start or stop. We had to figure that out. All right. All right. Area between curves. We're going to use that then to revolve solids later on.